Hey guys, Mr. Stevenson here. I've decided that I was looking at the formula book and all these formulas here, and I was thinking, like, if you guys have not even seen this stuff, if you did not see this last semester, then these formulas are just going to be completely meaningless to you, and it's going to be hard for you to even do a lot of the problems regarding this on the IB test without at least understanding where these things come from. So I thought, let's do a very rapid introduction and analysis of 5.5, 5.7. Try to get this done in about 2 weeks, and then we're going to jump into review, and if we can review some stuff as we go, then we'll do that as well. All right, so that's what we're going to do, and we're going to look at the chapter from the book, which I'll just go over it and kind of explain it to you because it's all there. We're looking at chapter 25. And we're just going to dive into this, and I'll try to explain how it goes, and we'll look at some examples, and you can do some practice problems. All right. So, first one is we need to be understanding. We need to understand what random variables are. Right. So, you probably we can just look at this. Random variable is a no, it represents a number, and it represents possible outcomes which could occur for some random experiment, right? It's best done with an example. So there's two types we're going to talk about: discrete and continuous, and these relate exactly to, discrete graphs and continuous graphs, right? Discrete graphs look like this, where there's discrete dots, and continuous graphs look like this, where there's a straight continuous line, right? And the variables for these are same definitions, right? Discrete random variable has distinct possible values, right? For example, it could be number of houses, right? You cannot have like half of a house or a third of a house or a fourth of a house or 1/100th of a house, right? You have to have integer values, right? So you're thinking like these are integers, right, for discrete. So like sequences are discrete, whereas functions are usually continuous. Number of bicycles, right? You can have 1, 2, 3 bicycles. Really good intuition here is if it's discrete, it's something that you can count, right? It's something you can actually count on your fingers. Continuous could take any value in between, any value on the number line, right? So it could take 0.1, 0.2, 0.3, 1.5, 1.65, any number on the number line, the variable could take on those, right? Really good way to think about this is something that you need to measure, right? So it might be heights, it might be volume of water, it might be time. Any of those things are going to be continuous random variables, right? And random variables have what we call probability distributions. What that basically means is like we can represent their probabilities using a graph, right? So certain probabilities for discrete variables might look something like this, where the probability of this event is maybe 0.1, and the probability of this event is maybe 0.2, and basically it's just saying the distribution of the probabilities can be analyzed. And for a continuous graph, you might see, or for a continuous variable, you might see something like this, where it's like if I want to know the probability of event A happening, I might just look here, and it might be like, oh, the probability of event A is 0.2, and so distribution just means there's like a shape to the way that the probabilities are looked at, and we'll talk about that in a second. Notation you have to understand is the probability that random variable x takes value, again, little x, is denoted like this, right? So we're saying x is our random variable, the thing we're looking at, and we're saying the probability that random variable takes on this value is given, and this is the notation for that, right? So like you might actually end up with like, some sort of probability here, right? This is really good to look at like an example, right? If we're flipping 2 coins, right, the possibility are heads or tails, right? And there's a couple things that could happen, right? What's the sample space? What are all the things that could happen? Well, you could get heads, you could get heads, tails, you could get tails, heads, and you could get tails, right? In this case, we're gonna say that x, the big X, is number of heads, right? And so if we write probability that x is 0, right, we look at this and we say, what's the probability that I get 0 heads. Well, that's only this one, right? It's 1 out of 4 cases, right? So the probability that I get 0 heads is 1/4. And likewise, you can see the probability that I get 1 head is these two, right? There are 2 cases where you get 1 head, heads, tails, and tails, heads. And so that's 2 out of 4, or 1/2, 50%. And so you can see the last one was the probability that I get 2 heads, right? This is 2 heads, and that's this one here, right? It's only one that has 2 heads, and the probability of that is 1/4, right? So that's what the notation is meaning, is you define a variable, x is the number of heads, and then this is saying the probability that the number of heads is 0, the probability that the number of heads is 1, the probability that the number of heads is 2, right? And from this, we can create a probability distribution, which is basically a graph, right? Which, again, down here you have a variable, which is x, number of heads, right? And then up here we have our probability, and you just graph it, right? So this is just probability of 0 is 1/4, probability of 1 is 1/2, probability of 2 is 1/4. And that's called a spike graph. You could also have a probability column graph, which is the same thing. It's just like a bar graph. It's just showing that, again, this is our variable x, number of heads, and the probability for each one. Okay, let's look at another example. We're going to write a probability distribution for the sum of 2 6-sided dice. First thing we want to do is define what is x. What is our random variable? Is it discrete or is it continuous? And in this case, x is the sum of the dice, right? And so we want to think, okay, can the sum of the dice be any number on the number line? No, the sum of the dice, you have to be 2, 3, 4, 5, 6, blah, 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 right? So let's think about, what is the sample space? What are all the possible values of x, right? What are the values x can take on? Well, it can't be 1, because you're rolling 2 dice, right? These dice are like 1 through 6, right? You can imagine little cubes. Hopefully you know what these are. Same thing they use in that holiday that we did, bobbing, right? The same dice that they use there, right? So the sample space for adding the dice is the lowest one they could have is 2. And then you could have 3, 4, 5, 6, 7. These are all the sums if you add the dice together, right? 8, 9, 10, 11, 12. You can't go anywhere past 12 because there's 6-sided dice. The biggest side is 6, and 6 plus 6 is 12, right? So that's the sample space. These are all the possibilities that x can take on, right? So then we might ask the question, well, what is the probability of x equaling 2? Right? So what is the probability that the sum of the dice is 2? That's what this is saying, right? And so what might help you is to actually write out the sample space of all the dice, which is this, right? And you can see these are all the possible combinations of dice. The probability that the sum is 2 is there's only one of these, and there are 36 total probabilities, right? There are 36 total outcomes, right? And this is 1 out of 36. The probability that x is 2 is 1 out of 36. You might then ask, okay, what's the probability that x is 3? And that's going to be, okay, well, there are 2 3s. So that's 2 out of 36, or 1 over 18, right? And you could write out all the probabilities for all the sums, right? And 4 is 1, 2, 3. So it would be 3 out of 36, blah, 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 right? And then this is basically what you use to create your probability distribution, right? We would then come over here and graph. Okay, well, we're going to start with, there's no, like, the probability of 1 is 0, so we're not going to do that. I'm going to do a spike graph, right? And here we're going to put our sum, and here we're going to put our probability. The probability of 1 is 0. The probability of 2 is 1 out of 36, which you could figure out what the percentage that is. I'm just going to write 36 up here. 18, 9, 3, 1. And then the probability of 3 is 2 out of 36, so that would be here. The probability of getting a sum of 4 would be 3 out of 36, which is there. Probability of getting a 5 would be 1, 2, 3, 4 out of 36. Right? And you do a little bit higher, and so on and so forth, right? And you'd be creating this graph that represents the probabilities depending on your random variable x, right? Your x is the sum of the dice, and you would end up with a graph of the probabilities of each one. Okay, and if you did it as like the bar chart kind of way, it might look like this, right? Your probability of getting a 2 is 1 over 36, which is equal to whatever that is there, and so on and so forth. And what's interesting about this that we'll talk about later is this is very normally distributed, right? It's symmetrical about the middle there, right? About the average piece. So that's what a probability distribution is. It's just finding all the probabilities of all the possible outcomes and then graphing them according to this chosen variable. Okay, so now that you know that, you should try the exercise provided for this section, which is 25A. Basically just trying to figure out what is the random variable and is it discrete or continuous, and what are some possible values that it could take on. Especially I'd like you to consider number 4, which is actually going through this again with a coin. All right, so please try those so you can get experience with it. Okay, so there's a couple of rules or general guidelines as we assign probabilities to these. One is just notation-wise. This sample space is denoted with like x1, x2, x3, such, and so on and so forth. These are just saying these are the possible values that it could take on, just like our sum in the previous example was, 2, 3, 4, 5, all the way to 12, right? You're just listing out what are the possibilities, and the corresponding probabilities are here, right? You can think about this as like the domain, and this is kind of the range of the probability function, right? And so the range would be like, oh, well, this one was 1 over 36, this one was 2 over 36, blah, 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 blah. It's just the corresponding, the probability of x1 is p1, the probability of x2 is p2, so on and so forth, right? And then again, just the notation that you're going to see is, the probability of this random variable being the sum of the dice is whatever, x, 1, 2, 3, whatever. And then this is the probability it's given. And then notice that these I values, the subnotations should be positive integers, 1, 2, 3, and so forth, right? So a couple of things. One is the probabilities, any individual probability, any one of these has to be between 0 and 1, right? You cannot have a probability in there that's bigger than 1, right? There's no such thing as like 110% probability, right? All probabilities are between 0 and 1. Next is if I sum up all my probabilities, I should get 1, right? If I consider all possible outcomes, then any of those outcomes has a 100% chance of happening, right? Like if I added up all these individual properties, possibilities, I should get 1 out of all of them, right? So because that's all the possible things. And then what it's saying is that the probabilities themselves describe the probability distribution of x, right? So if I graph, basically I would graph x1 versus p1, right? So like not x1, xi versus pi. So x1 would correspond with p1 and x2 would correspond with p2, right? And that would tell me my probability distribution. Right, so important things is no probability can ever be greater than 1, right? That's what this says. If you add all the probabilities, you should always get 1. This is telling you all the possible things that could happen, and then just notational stuff, all right? And then a couple more things that you probably already know. The mode of a distribution, it's its most frequency occurring value of the variable. So, for example, the mode of this one is here. This is the most frequently frequent one, which in this case is 7, right? You can see that here. 7 is the most likely outcome for adding 2 dice together, right? So that would be the mode. The other one is the median, is the middle value. It will be whatever, that value that is in the middle, or whenever the cumulative value reaches 0.5, right? So if I started adding up all these values, 1 over 36 plus 2 over 36 plus 3 over 36 plus 4 over 36, as soon as I got to 18 over 36, I would be at my median, right? Because that is the middle value. Okay, so another example is this magazine store that is recording the number of magazines purchased by its customers, and it somehow collected the probabilities that each that they purchased 1 magazine, 2 magazines, 3 magazines, maybe probably just by collecting data of, every time somebody comes in, they record how many that they buy. Okay, so so in this case, the random variable is the number of magazines being purchased, right? So X is the number of magazines. So you could then write the sample space, right? Like this is the X1, X2, X3. What are the possible numbers of magazines that they purchase? Well, they could purchase 1, 2, 3, 4, or 5, right? So that's the sample space. These are the xi, right? So this would be x1, x2, x3, and then we want to figure out what are the pi, right? What are the corresponding probabilities? Well, the probability of 1 is 0.23, the probability of 2 is 0.38, the probability of 3 is 0.21, the probability of 4 is 0.13, and the probability of 5 is 0.05. And you can even just make a table out of that. Right, if you had organized it, if I'd organized it a letter. And if it did that, that would be our table, right? So this is the answer to that one. And then graph the probability distribution. That is, you just create a chart with x on the bottom, right? So you're just graphing these values basically, right? You get x is down here, probability is up here, and you can see if you graph it, you get this general shape. And then if you state the mode is the highest one, so the mode is 2. And the median can be found by doing this, right? You add up the probabilities until you reach 0.05, right? So P1 is just 0.23, so the median is not in P1. If you do P1 plus P2, you get 0.23 plus 0.38, which is 0.61. And since 0.61 is greater than 0.5, that means as soon as you reach something greater than 0.5, that's where the median is. So the median is also in 2. Right? And then the next piece is we're just trying to show if these are probability distribution functions. If you're trying to show that they're probability distribution functions, then they have to meet this criteria, right? Every single probability must be between 0 and 1. And if I add up all the probabilities, then it must equal 1, right? So basically what I'd do is I just calculate the probability, right? I'd say, what's the probability of 1? And that would just be plugging in 1, right? That's going to be 2 over 34. Then I'd say, what's the probability of 2? You plug in 2 and you get whatever that is, the probability of 3. And what you want to make sure is that none of these probabilities are greater than 1. And then if I add them all up, right, if I add up probability of 1 plus probability of 2 plus probability of 3 plus probability of 4, I should get 1. I should not get 0.8, 0.9, whatever. I should get 1 for every single one. So you'd have to check that, right? Same idea here, right? This is a probability. We're trying to check if it's a probability distribution function. So I would plug in 0, I'd plug in 1, plug in 2, plug in 3. I would check first and make sure no probability is greater than 1 or less than 0. And third, make sure if I add up all the probabilities that I will get exactly 1. And you can see, we'll just look at this so you can see what it looks like. But for the first one, you get probably like 2 over 34, 5 over 34, 10 over 34. Every single one, none of them is greater than 1 or less than 0. If you add them all up, you get exactly 1. And the next one, if you do this, you end up with probabilities of 0.064, 0.288, blah, 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 and this sum is 1, and so that is also a probability distribution. If you're confused about this notation, please go back to chapter 8, and it talks about what that means, right? Okay, so that's it for this. Again, you should try these problems here in the textbook. And there's one more example here that's pretty straightforward using marbles. You should look at that and then try these problems as well, all the way up to 12 after this video.